start recording with my quorum. So welcome back. Happy Thursday before break. It's a lovely day outside, another day without my coat, walking from the parking lot. I have this up because I was just asking folks offline whether they were available on May 6th. So if you're not sitting here in front of me, either on the screen or here, I will be sending out an email to collect that additional date, because that way we'll have more time to ensure that we can finish Unit 5, which I think most of you are going to end up needing to do your project. And we'll see if I can fit any of the extra stuff in that I thought I might have time for and didn't end up doing that last year. So today we have, get to the picture again, this model to go through, and this one, hopefully. So I want to back up a little bit and just sort of remind us what we're doing with respect to the invariance constraints and all that stuff, since we went through that. Share screen. What a great idea. There we go. I had barely gotten started, though, in my defense. All right, example 4B is where we were. So the story here, we have 3 indicators of a latent construct at 4 different occasions. We want to see if the construct itself is showing change over time. That's the story. So we're thinking of these indicators as really like one idea that's measured 3 different ways, as opposed to 3 different measures, which is the alternative way of thinking about it that we'll end up with. But the first step that we had to do had nothing to do with longitudinal analysis, right? It's the factor analysis class. The idea of testing longitudinal invariance, folks, what does that mean? If you were to explain it to someone.
The parameters are measured separately over time, or estimated separately over time.
In the configural model, yes. That's what we start with. And what is the point of going through these various model comparisons where we put constraints on things and see what happened in terms of testing invariance? Oh, Kendall's here. She's not going to join you guys. We got 4 Zoomers and 2 Roomers. What's the point of this? That's my question to you.
Is it to look at, like, if the items are similarly related to the trait over the study period, over time?
I would say that, yes. What were you going to say?
To make sure you're measuring the same thing over time.
Measuring the same thing over time. So in terms of the factor loadings, those are slopes of how the trait predicts each of these outcomes. We want them to be the same over time because that conceptually defines what the factor is. So we have block design as a measure of abstract reasoning, digit symbol substitution as a measure of processing speed, and prose recall as a measure of memory. Like if cognition became more of one thing over time, then thinking of it as cognition as one thing is a little bit tenuous. And this is something you kind of have to argue for. Like you can cite evidence in terms of loadings, but you also have to try to make an argument as to the name that you're giving the circle means something. And so that's a validity argument, essentially, at that point. If this is really measuring cognition, then it should predict these other things in this way, and this is how it should behave over time, all that stuff. But loadings being the same over time helps us to ensure that the factor is conceptually defined the same way. What's the next step? Starts with an I in terms of what is being constrained. Intercepts, ding ding. So configural is no constraints. Everything's on a different scale. Then we have loadings, which is called metric invariance or weak invariance, depending on who you read. Those are all synonyms, so that was in here. Intercepts, then, we're getting to, I think that was green, maybe? Yeah, green. Intercepts is scalar invariance, or also what is known as strong. Another set of synonyms. Now, why do we want the intercepts to be the same over time? And if you don't want to talk, you can use the chat. And if you don't want to talk, you can gesture. Or you can log into Zoom and use the chat. I do have people do that. Why do we want the intercepts to be the same over time? If we don't know, then this might be a good place to start. I'm seeing some hesitancy, sensing some hesitancy in the answer.
I wouldn't mind going over it again.
Can we go over again?
Yes, please.
Okay, I can do that. So we'll start here. Scalar invariance. Each observed outcome, so the 12 variables that we have here, is going to have one factor loading in this model, one intercept, and one residual variance. So intercept means the same thing that it does regardless of what class I'm teaching. It is the expected outcome when your predictors are 0. That is always what it means. In this context, your predictor is the factor. So what we want to be able to say is that if somebody has a factor score of 0, which is the mean for the sample in the way that we've set up this model, then they should have the same predicted outcome regardless of what occasion it is, because what matters is that they have a factor score of 0. So we want to be able to say that the reason that it looks like the means of these outcomes is declining over time is because the factor itself is declining. And once you control for that or allow that to happen, then the indicator intercepts for the expected outcome at a factor score of 0 should be the same. So I mentioned this last time, and I will mention it again. A lot of folks will call these the means of the indicators instead. That is not correct. It works out in a standard factor analysis that if you set up the model so the factor mean is 0 as your method of identifying it, then the indicator intercepts become the indicator means. It's essentially like you've mean-centered your predictor. But if you set it up a different way, like we're going to have to do here, then they're not the means anymore. They're the intercepts. They're conditional means. So when I teach this, I make that point because I know this distinction is coming. Because usually at first, students are like, well, why should the means be the same over time? Isn't that the point, that we're examining change? Like, why is that a reasonable expectation? It's like, no, the means don't have to be the same. The intercepts do. Conditional means at a particular factor score. Okay, does that part make sense? Okay, so it makes 0 sense to move forward if we can't constrain at least some of the intercepts to be the same over time, because that means that there's not a single thing that's driving change. Each of these is sort of changing in its own way at a different way. So then that becomes problematic in terms of thinking of one thing as a latent factor changing. So to do this, let me review actually the constraints for the loadings here. When we constrain the loadings to be the same, which we did in the earlier step, what do we have to free at the same time? And you can look at the picture or you can look at the code. Take your pick.
The covariances?
Close.
Factor variance?
There we go, factor variances, yeah. So we're saying that the only reason the loadings were different is because the factors that they connect to had different variances over time, and that's what was screwing up the loadings, because loadings are unstandardized. So we would free the factor variances at the non-reference occasions. So this model is set up so that the factor variance is 1 still for identification. Now all the factors are on the same scale with respect to the loadings and the variances. So we're freeing the variances at the alternative occasions, keeping it fixed to 1 at the reference occasion. That way we can test all of the loadings being equal over time. Okay, now at this stage, where we are currently, we're constraining the intercepts to be the same over time so that we can say the outcomes have the same expected value, conditional on a factor score, regardless of which occasion it is. What do we have to free in order for this to work? Factor means. So we're allowing change in the indicators through the factor only. So if they all sort of change together, allowing factor mean change should make that fine. So we've added in these green paths here. Do the thing. Apparently I didn't save it. There we go. And we've estimated the factor means here. So at this stage, now the model is fully linked together across occasions with respect to the intercepts and means and with the factor loadings and variances. So think of those together. Loadings and factor variances go together. Intercepts and factor means go together when you're setting these things up. And at every stage, we've allowed all the covariances to be whatever they want. That's a typical thing, and it's a reasonable thing. So what are we looking for as evidence that these constraints are acceptable?
It's our fit indices, right?
Yeah.
So one of the ones we were talking about was the chi-square
Yep.
and the log likelihood.
Yeah, and the log likelihoods. So which one is our model?
We're the hub.
We're the hoe. Yes, never forget that. So this chi-square right here tests the difference in -2 log likelihood, rescaled by the scaling correction factors that are given here. So this looks pretty good, actually. Model's still non-significant, meaning that it is non-significantly worse than perfect. So good enough is the way I would interpret that. But this is the fit of the overall model. If we want to test the constraints specifically, then we need to compare it back to the previous one and see if we made it not worse. So in this comparison, which I did using Excel, the chi-dist function, it gives you an exact p-value for any chi-square on 6 degrees of freedom, because we constrained the loadings to be 3 instead of 12, but then we had to give back 3 factor means. So we have a net change of 6. It's happy. None of the modification indices said any of these were a problem, so we can move on. So the next step then doesn't have a special name other than strict invariance. So we have weak, strong, strict is analogous to metric, scalar, residual variances. Residual variance, invariance. Seriously. And that one's blue. So now we are asking the question, is the amount of the indicator's variance that's due to something other than the factor different over time? We'll go through the process of doing it, but it's sort of debatable importance. There's some methodological literature. Hey, come back here. There we go. There's some literature that suggests that if you don't do this, that can sort of propagate to other areas of the model and cause problems, but I don't know how widespread that is in practice or how non-invariant they'd have to be. So I would recommend going through this step, but if it doesn't hold or it doesn't hold completely, I don't think that's necessarily a deal breaker. I think you could probably make an argument that you did what you could to constrain as much as possible. So at this stage, we're fixing the residual variances to be equal for each indicator across time. Is there anything we have to do with respect to the factors at this step? Because when we fix the loadings, we freed the variances. When we fix the intercepts, we freed the means. Now we're fixing the residual variances. Do we free anything? Said differently, do you see any new periwinkle blue up here? Nope. No, we don't have to do anything. So this should be a change of 9 degrees of freedom to do this. And we're going to leave the covariances alone. Theoretically, you could try to constrain them, but no one ever bothers. So model fit is still, actually, nope, model fit is not good anymore. Now our model is significant. It's unhappy with us. The model on the whole is still within what most people would consider good fit, but a model comparison against the last scalar model says, nope, we broke something. So this is the point where you would look through your list of modification indices and ask which ones broke it. And you're not looking for all possible modification indices. There will be many, many, many of those that are trying to help you fix your model atheoretically. We are only paying attention to the ones that represent constraints that we put on the model that caused it to break. That's the idea. So we are looking for the change in the chi-square that would be predicted by freeing these particular variances. So if we freed the variance for block design at the first occasion, then the chi-square would improve by about 22, and the variance would be higher by about 4. So I would normally do these in 2 separate steps, but I'll do them together to save a step, because why not? The handout's already 25 pages long. So then I introduced what is known as partial invariance. So I'm allowing the block design residual variance to differ at the first occasion, allowing the digit symbol one to differ as well, but then the others are still constrained. So you can have sort of hybrid models like these as needed. Survey says, now it's not worse than scalar, hooray. So at this point, now we're going to head back to the longitudinal class, okay? Any questions before I head back there? All right. Oh,
Wait,
please.
sorry, I have one question.
I didn't wait long
So you're
enough.
talking about how in general for these different traits to be represented by the same factor, that like you wanted them to all be sort of changing in the same direction, like they're all going down.
Yes.
But I don't know, I just think of like something like intelligence where some sort of score on a scale, like higher could be better, lower could be like representing more intelligence in some way. So I guess if they're like perfectly sort of like like one is going always up and one is going always down, do these sort of models work for that in terms of like if I had different factors that all sort of represent more intelligence, but the score is higher or lower, but that represents a different thing? Does that make sense?
Yes, I think you're asking if some indicators higher is better and some indicators lower is better, but they all measure the same trait. Is that still going to work? Because then lower is better would hopefully, if they're growing, decrease over time. And if higher is better, then they should increase over time. And your question is like, can that be a thing? Okay, yes it can. Theoretically, there's no problem with that because what would happen is that the loading for the one that's going in the opposite direction would be negative instead. And so then it could work because you've essentially inverted it. However, in practice, then you can run into model convergence problems, particularly if you're in Bayes land, because the model doesn't know which way is up. So if I have two indicators that should be positively related and two indicators that should be negatively related, then I could have positive signs on these and negative on these, or I could have vice versa, and it's an equivalent model. The difference would be what a higher factor score means and whether it's going with the positive indicators or the negative indicators. And I've seen that break. So if you wanted to do that, I would probably recommend reflecting the data ahead of time, like times it by -1 so that everything is going in the same direction, and then growth would be consistent in direction as well.
Thank you.
Sure. The other way you could do that is by fixing, putting a constraint in the model that the loadings for the direction you want it to go have to stay positive. And so then it will force it into that orientation as to which way is up. Okay. Other questions or clarifications I can help with? Okay, so we're ready to head back to longitudinal class, right? Okay, here's how we're going to get there. Ignore the measurement model. That's dead to us. We don't care about that anymore. We've set it all up. It's all constrained. It's all lovely. It's done. Here is what we have to work with. These are our 4 outcomes that we're going to examine change over time with, the factors. So just keep that in mind. These are your observed variables at this point, except they're latent. Otherwise, it's the same thing. So this model then is not estimating the mean at time 1 and not estimating the variance at time 1 because these are fixed to 0 and 1 for identification. This is setting the scale of what this variable represents. It's in the key of z. However, at the rest of the occasions, they get whatever mean they want. And because time 1 is set to 0, these means are going to become mean differences relative to time 1. Because 0 is what the mean at time 1 is. So this will essentially create a slope that differentiates time 2 from time 1, time 3 from time 1, time 4 from time 1. Does that sound familiar? What did I call this idea last semester? Saturated means. Yeah, that's what this is. Likewise, other than the variance being forced to 1 for identification at time 1, all the variances get to be whatever they want. Wait for it. And all the covariances get to be whatever they want. What did we call that last semester? Unstructured. So this is the answer key model against which we are going to see what happens with respect to change over time. So in terms of the structural model, this is as good as it gets. Unstructured with saturated means uses all possible parameters that are available in terms of your degrees of freedom. It is essentially the H1 model of your structural model. So now we put constraints on it essentially by saying, hey, can I predict these means over time using fewer parameters? Can I predict these variances over time using fewer parameters? And can my random effects capture all the reasons for covariance among these things? Same set of ideas, except we're jumping sort of ahead rather than doing like an empty model and then a fixed linear model, and then a random linear model. Like, we're jumping ahead to just the random change part at this point. But we can look at the results to try to guide us as to what kind of change we might have. So if I look at, let's go to the means. So the mean at time 0 is 0, or time 1 is going to be time 0. There we go. These ones, though, are not. So because this is 0, this is interpreted as a change. On average, at time 2, cognition is lower by that much. On average, by relative to 0, it's even lower, and I have the rate of change computed here between 1 and 2 and 2 and 3. So does this type of change look linear to you? We go from a difference of 0.11 to a difference of 0.15 to a difference of 0.22. No, it looks like there's kind of a non-linearity where it's getting more change over time. I only have 4 occasions, though, and a quadratic is going to be kind of pushing it. So this is where latent basis would be motivated, by this idea that there's some non-linearity of the change, but it's not like we don't have enough occasions to fully capture it with multiple types of random effects. So this would point towards that. We have, let's see, where's the variances? Are they down here? Yeah, here's the variances. Do they look the same over time or different? You can just eyeball it. And they look kind of different. Are they kind of randomly different or like different in a pattern? Definitely in a pattern, right? There is a bigger gap between 3 and 4 than between 3 and 2. So maybe the variance is increasingly in like maybe a quadratic pattern over time. Yeah, that sounds like random linear to me, or random slightly nonlinear is what we're going to end up with. So different variances over time are an indicator of individual differences in change. Otherwise, if variance were the same, that indicates parallel trajectories where you have intercept differences only. So both of these patterns merit some kind of what we're going to call a higher order factor, what we called last semester random effects, to explain average change, the fixed effects part, and then individual differences change, the random effects part. And covariances look like they are in covariance things. So where'd we go? I lost them. Here they are. So we have fairly strong covariances over time. I could convert these into correlations if I wanted to, but that's not really relevant. It looks like we have a lot of commonality over time. That's my point. Okay, are you ready to model this now? We're here, let's do this. So latent basis. Now I told you that our previous model was scaled in the key of z, right? That the variance at time 1 was 1 and the mean at time 1 was 0. I want to keep that scale. The problem is that I can't force the variance at time 1 to stay 1 because it needs to be free to become leftover level 1 residual variance that is unexplained by the level 2 random effects. So I have to sort of cheat it. And that is why in the measurement model, I still have all the constraints, but instead of having it find what the loading would be, I fixed it to what it was in the previous model. So this will then recreate a total variance of 1 for these factors, for factor at time 1, and then it will be partitioned into level 2 stuff and level 1 stuff. But the total will stay 1 like it was in the other model. And because I used the same number in all these spots, it's still a constrained loading the same as before. We don't have to worry about that with respect to the intercepts. At this point, we can keep the mean at time 1 in 0, and there's no additional information to be captured. It's sort of an arbitrary point anyway. It's your baseline, whatever that means. So then in the structural model, we have shut off all of the factor means. The first one was already shut off for identification. The rest of them are now shut off too, because these aren't factor means anymore. They're going to be intercepts, conditional means, the expected value when the factors are 0. Well, we want the factors to capture any changes in the intercepts or means over time. So we have to shut them off, so that information has to go up to the factors. So these are fixed to 0 for identification of the random effect factors. They have to be. Likewise, to draw a parallel with the typical R matrix that we've been using, such as an Elmer as its default and only choice, we have the level 1 residual variances held equal over time. So these are going to be the leftover parts of the factor variance after being predicted by the random effects. So this is level 1 res var, and if do I have enough time? Yeah, I have enough characters. I could have done that. But I think I put it in here maybe. I try to label these sorts of things when I can.
I have a note that it's also the overall residual variance. Is that incorrect?
In this model, it means residual in both ways, because
Got it.
this is level 1 residual in the way that we talk about it. It's also left over
Got it.
in that way.
Okay.
Because it will have been predicted by a fixed intercept and fixed slope. So it's left over in that sense. All right. Then, covariances. Those are shut off here because those would represent the off diagonal of the level 1 R matrix. We're saying the only reason that these outcomes were correlated is because of the individual intercepts and slopes. Once we control for that, there is no more correlation. That's a testable hypothesis. So we'll see if model fit is potentially dampened by this constraint. But I think it's a reasonable place to start. Likewise, I think starting from all the residual variances at level 1 being equal is a reasonable place to start, because heterogeneity of variance is supposed to have been captured by the factors. So if you put the factors in to do that and you let the residuals try to do that, there's a redundancy that can cause problems, particularly with only 4 occasions. You do not see that very commonly, though, in books and articles teaching you about how to do this. They start from the opposite perspective, but I have a different opinion. Okay, so all we've built so far is an R matrix. That's what we've built here, level 1. The intercept thing is not something that we ever had to think about before, but because there's these variables underneath it that we're pretending aren't there, we have to think about this step. Okay, questions? All right, so in the gray box then is the new part. It's in purple up here. So now we have circles predicting the circles. I have int and slip because slope. It's not lin like it was or qua because that's not what it means. This is going to be a latent basis model. So I am defining my intercept factor the usual way because U0 in your equation doesn't multiply anything. So there's an implicit 1 that it does multiply that this is essentially enforcing. So I am defining this factor so that I can interpret it as an intercept by forcing these constraints on it. Likewise, slope, I am defining the loading for that onto my outcome at time 1 at 0. That then tells me that the intercept is going to represent the expected outcome at the first occasion. I am fixing the loading for the slope factor at the last occasion to 1 to represent some total amount of change. So in terms of time units, because it's change per unit time, the entire study is the unit. Alternatively, if you don't like that, you could do at 1 here and then free the last 2 so that a unit is still 1 unit in time between occasions. Alternatively, undo, undo, undo. You wanted to keep it in per year change but have the middle ones free, you could do something like this. So there's 4 units in time across the entire study. This way is useful if you want to compare against like a linear model, because essentially what happens at that point is you would be testing whether you can force that to 1 and force this one to 2. And if you can force them to 1 and 2, then linear is sufficient and you don't need estimated loadings. So it's a way of testing for nonlinearity explicitly. If you ask it, hey, if I make this linear, does the model fit worse? But I had a 1 here, so let me change that back, following the most common way of doing this. The fixed intercept has to be 0 because we don't have any additional information with which to estimate it, because the This 1, 0 here is the end of that story. So our fixed intercept is forced to 0 for identification. This is not. What is that? It's in brackets. It says slip. What would I have called that last semester?
Fixed slope.
Fixed slope. Fixed whatever kind of slope, we don't know yet, but fixed slope is the answer. Yep, the mean of the slope factor is what we would call the fixed slope. What are these? The variances of the factors. Random effect variances. And because I have two random effects for the same person, I also need their covariance. So we just built G. A 2x2 G matrix at level 2 is what we just built, with fixed effects right here. Okay, how are we doing? It's better? A little better? It takes a minute to wrap your head around this. It really does. Now, the fun part comes in interpreting this. This is the super fun part. That's sarcasm. So we saved 6 degrees of freedom relative to the answer key saturated means unstructured variance previous version of this model. How? Well, we had 3 factor means before that we've replaced with 1 fixed change slope. So the question then is that slope do a good enough job to recreate the means that we can have a more parsimonious structure? We had 3 factor variances and 6 covariances. Those are being replaced by 2 estimated loadings, 1 intercept factor variance, 1 slope factor variance, and then the covariance between the random effects. So then that's a net change of 6. So this is another question of not worse. When we did this last semester, we did it in pieces. We did, does the means model fit? And then we did, does the variance model fit? Why did we have to do it separately last semester? Do you remember? REML. Yeah, models that differ in fixed effects are not comparable under REML. So we couldn't do the means part in REML. We had to put in, remember what we did to do it? Yeah, REML, good Zoomers. Do you remember how we did those tests? It's been a minute, I know.
Was it the linear combination?
Yeah, we stuck in a bunch of dummy codes, and we tested if the set of dummy codes helped the model, like plugging in all the holes around the trajectory. Spoiler alert, that's what we're going to do today too. It's the same idea, just in a different framework. Likewise, this part then would be, is unstructured necessary, or does this do a good enough job? So on the whole then, the question is, did we make it worse? The model itself looks like it fits pretty good still. And some might argue, it's fine, write it up and turn it in. But I'm trying to teach you the rightest way to do things, so. The answer is slightly worse. So now the onus is on us to figure out where the problem is. Turns out, it is this. So modification indices that are relevant with respect to the constraints that we've placed, it's the mean at T4. And note that it doesn't even help you. The label of this is mean interceptor threshold. You figure out which one it is. It's the intercept. So this tells me that if we allowed the intercept for our outcome at time 4 to be estimated rather than fixed to 0, the chi-square would improve by 10, and it would take on this value. So in other words, the change in fit was about 13. 10 of that is because of this one problem. So I think this is something we should probably pay attention to. So here is the solution then with respect to just the part we care about. So I didn't print the whole measurement model because that's not relevant to the story at this point. So here's my fixed loadings for my intercept factor. Here are my fixed and estimated loadings for my slope factor. So there's no contribution to the slope for time 1. At time 2, it's 0.27. At time 3, it's 0.63. and at time 4 it's fixed to 1. Now the easiest way to interpret this, as it states in the chapter I've stole the pictures from, is that this is the proportion of change that has happened by each occasion. So 27% of the change happened between 1 and 2, 63% of the change happened from 1 to 3, and then we have the rest of it here. Now what happens when these things go negative? That's when it gets tricky, and yes, I've seen that. That's when this whole proportion of change language doesn't work. Let me give you a different way to think about this. These are your new time values. That's what they become. Like, you know, in your data set, you would have like time as like 0, 1, 2, 3, 4. Well, if you scaled it so that all of the study was 1 unit, then your second occasion is time 0.27, your third occasion is at time 0.63, and your last one is at time 1. That's what's happening. And yes, that should hurt a little bit. The face is like, what?
I don't think I get that.
Let me, can I skip ahead? Okay, yes.
We can circle back if we need to.
In
that's
like
okay.
3 minutes.
Yes, that's fine.
I gotta just get one more piece and then I can
Yes.
show you how it works and I think it will make more sense.
Great.
Okay, yes. So we have our random effect covariance, happens to be not significant, whatever. The mean of the slip factor. What did we say that was?
The fixed effect.
Yep, this is the fixed time slope.
Yes.
So the fixed slope is negative. It should be. All the outcomes declined over time. So this is sort of like a sanity check, right? If this isn't negative and you're supposed to go down over time, stop.
Okay.
Something went awry. Like, this shouldn't be magical. This should be capturing what's happening originally in the 12 by 12 mean and covariance matrix that went into this thing. So the way that I would interpret this, given that a unit is the entire study, is this is the total amount of change between time 1 and time 4. The loadings tell you how much of it happened by that point. So they're the times in this case. So 27% of it, 63% of it. Factor variances, this is where most people would be like, they look significant to me. Not supposed to do that, but it's going to be fine. I don't need to do the likelihood ratio test to shut them off and prove otherwise. I'm sure it's fine. Residual variances, these are the R matrix. This is the diagonal of your R matrix that we constrained equal over time, and the model didn't have a problem with it. Okay. So given that this model doesn't fit, we're not going to interpret the results yet. We got to fix it. And I'm going to go with pink on here, because why not? Word only has so many choices for colors, and most of them render your text illegible. So, pink it is. So find the change. Find the pink text. I made my test easier.
You're letting T4 be free.
I'm letting the intercept for T4 be free. Yes. That is analogous to putting in a dummy code for T4 to plug the hole. And it wants that one plugged specifically. It's very particular about that. So I'm plugging the hole. So I only have 5 degrees of freedom relative to the saturated means unstructured variance model because I just gave one back. Model fit is back to good, not worse than the last model. So this one we can stick with. Hooray. So I got everything in here. Note that the loadings have changed for our slope factor quite a bit because now they're not the only thing causing change to be predicted by the model. We have the little dummy code that we stuck in to plug the hole that's going to do the same thing. And that is estimated right here. So you can think of this as like a trajectory deviation. How far off time 4 wants to be from what the intercept and slope means and variances would have predicted for it. It's an offset or a gap. So I made some pictures, and then I'll show you how I made the pictures. So I'm comparing the model predicted means for our outcome. Our outcome is a factor, but it's the same idea as we've done for, like in the Unit 6, I had 1,000,000 of these pictures. So the blue line, which is hidden, is from the residual invariance model, in which all the factors had separate means, variances, and covariances. So that was like our answer key. The orange one is from the first latent basis model, and the gray one is from the second. And so the reason that we can't see 4C is because it's behind the gray one. Like it's almost perfect. And the difference is, it's most apparent here, but time 4 is where the offset is. So it sort of changed the overall shape of the trajectory. And even though we didn't touch anything on the variance side, that has implications for what these predicted variances are as well. But on the whole, you would argue, yeah, that's pretty good. Now, where do these pictures come from? This is non-trivial. M+ will provide predicted means and variances for you. But if you want to know how it built them, which I think is instructive in figuring out the model, then we'll do it this way. So I added this anew from last time, given how many folks ended up with these models and being hella confused by them. It's not their fault. The model is hella confusing. So this part should look familiar. That's a standard level 1 growth model. So I have the fixed intercept plus the fixed slope times time. That part's normal. So the fixed intercept is 0 for identification because we're in imaginary factor land in the key of z. And note that it worked, by the way. The predicted variance at the first occasion was right around 1 in total, just like it was supposed to be. We have the slope mean, so that's my fixed slope. So it's negative. Highlight the correct number here. That is the overall amount of change. Then where time would normally go, I plug in the latent basis loadings. So that's what the factor loadings would have been constrained to set other kinds of change. So if I wanted to fit a linear model on a scale of 1 means the entire study, this number would be about 0.33. This one would be about 0.67. So they're not far from that, and you could actually test whether linear is enough if you wanted to. Okay, does that help a little bit? Maybe. It took a little longer to get there, but we're slowly nodding. This is why cameras are useful. Faces are useful. So the factor loadings in the latent basis model are your time occasions. That's what they become, to make some kind of nonlinear trend that is data-driven. Now this thing, we didn't really have before, but this is where the offsets would go to further moderate the curve. So the only one that uses it is time 4. So that's just a jump. The variances, slightly more complicated formula, but also familiar. The total variance at any particular occasion is the intercept variance, plus the slope variance times time squared, which are your factor loadings squared, plus twice the covariance of time with the random covariance of the intercept and slope twice times time, and then residual variance. So these are the numbers then from the output that build that thing.
Is time in the second portion of that also equal to factor loading, just to make sure?
Yes.
In the actual variant, or
This right here is the latent basis factor loading as
Right.
time, and then I just put the squared thing so that you can see that it matches, and it also shows up over here.
right.
Yeah, you're estimating occasions. Isn't that nuts? That's what it is, though. And last but not least, here's some words. So when you're reporting a whole bunch of factor models like this, it can be a lot more efficient to talk about fit in a table. So then you don't have to repeat these numbers in your text. You can just say, the configural model fit well, this model fit well, this model fit was equivocal. It's one of my favorite ones. You know what that means? Some liked it, some didn't. I tend not to try to use the specific labels like this is good fit, and this is excellent fit, and this is mediocre fit, because I don't want to fight with anyone about the words. Be like, here are the numbers. You label them however you like. But especially having, labels for these things that are either numbers or like as seen in table 1, rows 2 and 3. Like, tell your reader exactly what you're talking about, and they will love you. If you have like something like this here, so I have the RMSEA p-value was like 1 pretty much the whole time. If you have something that's going to be constant, like chi-square is always significant or something like that, you can avoid the extra table column and just put it in the note that says this is always this number. You don't have to for. So this is a long results section because I had to talk about the invariant stuff first, and then we talked about the change stuff, and then we talked about the latent basis stuff. So lots of words in this one. But hopefully that should make your life easier. And this is where it ended last year. So how are we doing last time? Thumbs up? All the way up? Or better than flat?
I think I'm conceptually just still trying to wrap my head around like what the numbers of the factor means mean. I think I understand. It's just like weird because it's like made up. Kind of. It's not made up, but it feels made up. So yeah.
Yeah, it does feel made up, but it's because we have this latent thing called cognition, and it doesn't have a scale. There's various other ways to identify the model that you could borrow a scale of one of the indicators, but I think that's potentially confusing because then what about the others? Like, then they're not adequately represented. So we have this thing that at the beginning of time is z-scores. So that's the scale that we're in. And yes, we're estimating time. See if I can say anything else that would be helpful. I don't know. I think I'm out of words. Again, these predictions that I made manually and plotted are given directly in the M+ output. If you ask for residual and Tech 4, then you will get model implied everything, and then you can make these pictures for yourself. And even though this is latent variable land, these are the kinds of pictures that you would put in a presentation or in a manuscript. You just have to be very clear about what the y-axis means. It's in the key of Z.
Could you go over just one more time what we would use Model 5B for? Like what, just like the general,
Yep.
the general umbrella.
Do you want a picture?
Sure.
Well, other than the pitchforks, what is it? Tridents?
Trident.
Yeah, other than the tridents and their use of squiggle too, which I find unacceptable. Because, this is an intercept. Like, put a label on it. Label these things. Don't do this to your reader. Anywho, what are we doing with this? We're seeing if cognition changes over time. That's the biggest level thing. Now, why would we want to know that? Well, we might want to predict who declines more based on your age, your health, your belonging to this group or that group. We might want to see if rate of decline during one period predicts some other outcome, like when you die, or how likely you are to be diagnosed with dementia, or Kendall, give me another one. She does aging research. Why would you want to know about individual differences in change in old people and cognition? Just make shit up, it's fine.
I don't know, something about like unhealthy aging, the trajectory of aging and how it might differ, which is kind of what we're talking about. Even like their ability to live alone.
Yeah, that's a good one. Yeah, who needs to be put in a home? They're unhealthy aging. That reminds me of my favorite Simpsons part. You know what I'm talking about? They're driving in the car, and Homer says to a grandpa, "Shut up, Grandpa, or I'll put you in a home." And he says, "I'm already in a home." He says, "Well, then I'll put you in the crooked home we saw on 60 Minutes. I'll be good." It's terrible, but it's hilarious. Yeah. So did that help? Like, that's what we're doing. And building up to this idea of a latent factor of cognition hopefully would better measure that latent construct than would any of the observed indicators that are somewhat fallible because they're imperfect, especially for speeded tasks in older adults. There's a lot of reasons adults can be slow, Most of them don't have to do with their intelligence. Even just, how quickly you can write with the pencil or hold a mouse, things like that. Okay. Other things for this? Now, the only reason we were able to do this is because measurement and variance held. What if you start going down this path and you're like, it's falling apart? Or things are changing in different ways for reasons that they shouldn't and you're not sure why? Do you take your ball and go home?
No.
It's like, yes, I do. You might be tempted to, but there's another game in town. New this year. I had to find another picture and steal it. Welcome to multivariate growth models. This is page 20. We're getting there. So this has a lot of names. Parallel process model is one that I've heard more recently people use. I just call it multivariate growth model because multiple things are going at the same time. You can actually force this kind of model into SAS, somewhat into Stata, and somewhat into R. But there are advantages to doing it this way. But conceptually what we have is, rather than talking about cognition at time 1 and cognition at time 2, I just have a model for like block, I've got a model for digit, I've got a model for prose. So mine would be a 3 trivariate model instead of multivariate. So like here's the intercept and slope for one outcome, here's the intercept and slope from the other. And this article's on your reading list if you want to have more detail. And they labeled theirs really good. Thank you, Emilio. He's one of his students wrote this, so. Because I'm sure he listens to my class. I'm sure.
One of your subscribers.
Yeah, the editor of multivariate behavioral research, I'm sure, is in my audience right now. Hi, Emilio. Nope. So if invariance breaks, or you're thinking about your data in a different way, like if you just want to know if kids improve in this outcome more than other kids, do they also improve in this second outcome more than other kids? Like if students improve in math, does that somehow translate into better improvement in language? Those are reasonable questions. So if that's what you want to know, then this is the better way to go regardless of whether invariance holds, because this is a more direct answer to that question. So what I'm doing first then is not a measurement model per se. It's a growth model, 3 of them. So I have 3 intercepts, int B, int P, and int D. I got 3 slips. I'm making them latent basis, sticking with that since we need some practice with that. I'm shutting off the indicator intercepts so that I force all of the information about their means and mean change up into the factors. I am holding equal their residual variances over time, because that is my level 1 diagonal of the R matrix for each. So essentially, like if each of these would be a 4x4 for one variable, I have a 12x12 R matrix. What dimensions would my G matrix be given this? That's what this is building. How many lines do I have highlighted? 6, there we go. G is 6x6. 3 sets of intercepts, 3 sets of slopes. R is 12x12. Actually, yeah, 12x12. I'm allowing indicators measured at the same occasion to have an additional covariance. So this is analogous before to allowing the same variable over time to have a covariance. This is the same times. So how you do at time 1 might be related regardless of which outcome you're talking about. Same with times 2 and 3 and 4. Building G then. Latent factor means estimated. Fewer words on the comments this time because I wanted you to tell me. What did I call this last semester? Come on, I gotta take the training wheels off at some point. I can't label everything all the time. What would I call this? What would you call this? Latent factor means for my ints and slips. Starts with an F.
Is it your fixed
Fixed.
intercepts?
Fixed intercepts and
fixed slope.
fixed slips. Yep.
Slips.
Yep. These are the mean changes. The mean total amounts of change in the way that I've set this up. Latent factor variance is all estimated. What would I call those? Starts with an R, although that's not as good of a clue. Random. These are my random effect variances around those means as fixed effects. And these are long. These are my random effect covariances. So this is where the big width thing really helps save some time. Otherwise, I'd have to write all these out, and there's like 15 of them. So annoying. Okay, good so far? This one's easier, isn't it? At least I think so. For right now, it's easier. I'm going to make it hard in a minute, but just keep in mind, if this was stuff that you could figure out on your own within 10 minutes at Google University, you would be wasting your time and your money being here. Okay, 48 parameters. I could go through and count them if I wanted to. Once again, which one are we?
We're the hoe.
We're the hoe. So the saturated means unstructured variance model is this one. That way, it does model comparisons against the right answer for you. Come on. Close this. No, it's trying to get in my header. Stop it. There we go. What do we think about the rest of the model fit? It's not as good as the other one. I think most people would be like, it's fine enough. I could go through the process of trying to make it better, but I decided that 25 pages was enough and that this was going to be good enough for me. But in practice, you might want to see what you can do to check local misfit. It might be that one of the residual variances wants to be different, something like that. You might need one of the offsets, to plug in the hole where the means trajectory doesn't work, things like that. So lots of output. So here's my intercept factors and their loadings. Here are my slope factors and their loadings. So kind of a common trend. It looks like actually prose has a little bit higher one than the others, but roughly linear with a little bit of nonlinearity. I would probably describe these because they would be equally spaced if it were linear. Then we get into covariances, whatever. We don't normally care about those. Same occasion covariances, don't normally care about those. There we go. Means. These are my fixed intercepts and slips. So now, Taylor, to your point, these numbers are interpretable. Doesn't that make you happier? It's not just like some random zero. So the mean for block design, according to the latent basis trajectory, is 10 at the first occasion. According to the trajectory, the mean for, prose? Why are these in the wrong order? That's odd. I must have copied and pasted something out of order. Let me fix it real quick. It goes in the order in which you define them usually. So you can hack that if you want them to appear in a certain order, but that looks better. The mean at the first occasion, as predicted by the trajectory for digit symbol, is 21, and the mean for prose at the first occasion is 8. So if you know what those measures mean, you should know what those numbers mean. It's nice and comforting. And what's happening with each of these things over time? They're declining. Now that is not good for this sample, but it's reassuring for us because that's what's supposed to happen. Now, can I look at these numbers and be like, oh, what the hell happened with digit span? It's declining like twice as much as the others. Digit symbol. Can't do that, right? Why not?
It's unstandardized.
These are unstandardized. So if you want to do things like that, you'd have to make sure these are on the same scale. But it looks like they're all declining to some extent. Intercepts fixed to 0. Here are the variances. Definitely intercept variance, likely slope variance is needed as well. Yeah, some sort of weird copy paste thing. I'll have to investigate that. Doesn't matter, but it bugs me. Here are my R matrix variances for each one, and then here are my G matrix variances. Now, the thing we care about, relative to the next model, relevant for the next model. Sounds like an airplane is about to go off in here. The heating and cooling just got really loud all of a sudden for no reason. And it's up to, I have no idea which one it is at this point. It could be either. Who knows? This building is so inconsistent. So this is Tech 4, is an option for output that gave me a correlation matrix of my latent variables. And I've highlighted the ones that we are going to pay attention to most. So do you think that people's individual differences in where they start are related across these three outcomes? Correlations of 0.7, 0.86, 0.78? Yeah, looks that way. Do you think how quickly they fall off the cliff, unhealthy aging or healthy aging, take your pick, is related across these outcomes? I would say yeah. So we have three outcomes. That means that we can have enough information to fit a latent factor for each. So that's the grand finale. This is a factor of curves model, where I'm going to dump factors on top of my factors, but they're in the opposite order. So let me pull up the two pictures side by side so that you can see. This is what we did first. Made a factor, watched it grow over time. Now we're making growth and then seeing if we can factor it. We're making growth first, and then we're seeing if there is a common intercept factor and a common slope factor that can explain the correlations among the intercepts and slopes. A factor of curves. So now we're going to throw more factors into the mix to do this. Here's the new part. Int ho and slip ho, that means higher order. Not you are the ho, HO model. So you can think of the intercepts and slopes as indicators. This is like a measurement model. The upper part is a measurement model. So just as in normal factor analysis, each indicator would get its own intercept and it would get its own leftover variance, we're having these here. But because it's left over for a factor, it's not called residual, it's called disturbance, because we need yet another name for the same thing. So this is analogous to indicator intercepts. This is analogous to indicator residual or error variances. So then we add the factors. So I have an intercept factor with all of the loadings estimated for each of the intercepts of the outcomes that are growing. I have a slope higher order factor with each of the loadings estimated, and I'm labeling them. So note these are three different words. That means there's no constraints. These are just labels. I'm doing that so I can do math on them. The higher order factor means are fixed to 0 for identification. Higher order factor variances are fixed to 1. And higher order factors are covariate. And I had some problems with estimation, so I'm forcing these loadings to be positive. It flipped the wrong way for some reason, and I didn't like that. So this is how you use model constraint, by the way, to force parameters to stay within boundaries or otherwise the direction that they want. You label it, and then you say, hey, can you make that thing greater than 0, where that thing is whatever this parameter is estimated to be. So I'm forcing the unstandardized loadings to be positive for the slope. Here's the picture. I stole their picture and modified it. So here's what I added. I have residual covariances for the same occasion. So this blue line essentially was connecting the residuals here, and it would connect them over here too. I also added an additional covariance between the intercept and slope of the same outcome, because I thought that was a reasonable thing. But otherwise, the correlations among the intercepts are now supposed to be captured by a general intercept factor. The correlations among the slopes are supposed to be captured by a general slope factor, and they get to be related. Ta-da! How'd we do? Model's still not happy. Fit's still pretty decent. Does it fit worse than the previous model? No. So this is good. It means that having a higher order intercept and slope adequately explained all of the covariances among the intercepts and slopes for each outcome. Here are the factor loadings. Standardize. So it looks like all three load on the intercept factor quite highly, all the indicator intercepts, as well as the slopes. So fairly strong support for some kind of common change here. here are the remaining correlations among the indicators, the same indicator, intercepts and slopes. And then in Excel, I showed, this is the original multivariate model correlations. These are the ones that are predicted by the factor of curves, and then I computed the discrepancy. So if there was any significant discrepancy in fit, like if we made it worse by doing this, this is where I would go to figure out why. And note that some of these are kind of far wrong. Like a miscorrelation of like 0.18 is kind of big. But each of these correlations is among latent things, so they have a lot of error to them in the first place. That's why I don't think it's popping as misfit, because there's a whole lot of error around that point estimate. And then here's some more words. We made it! Okay, take a breath. How are we doing? So big picture, you can see how factors grow over time with the first set of models. But if your factor falls apart over time, multivariate growth, and then see if it factors up here is an alternative. Either of these sets of analyses would be sufficient for your projects, by the way. You wouldn't have to do it all the different ways. Anyone thinking of trying this? Maybe? Like, yeah, I can do this. Good. By the way, I fully expect to have many meetings and email conversations with each of you as you work through your projects. That's just what's going to happen. But that actually is fine with me, because the time that I would normally spend preparing for class, I spend in conversation with you, helping you prepare for class. So I'm offloading my work onto you so that you can hopefully learn something. The feedback about the projects from the last time I taught this was everyone said I learned the most doing my project. They all said that. So I hope the same is true of you as well. Any questions?
When will we hear if we need to do changes to our?
Probably by Monday, or like after break. I'm gonna go through them this week, try to get the schedule built, and then, yeah, I know we'll send it back. I will either send it over email, or I'll upload it through the homework system and post it that way. I'll let you know when they're ready. All right, anything else? Then guess what? Have good weekends. Have a great week off. I hope you can at least relax somewhat, even if you're trying to catch up on work or other sorts of things. Let me know if you need anything, and don't forget you have formative assessment due the Monday we return. All right? All right, thanks for being here. Let me know if you need anything. Bye for 10 days. I know.